Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Syakir Irman bin Muhammad Kiranwa. My matrix number is 076579. And today I'm gonna talk about problem context in Smart Campus Navigation. For our case study, Smart Campus Navigation System for UNIZA, the problem is student and visitor across campus with real-time routine is guiding them into the optimal path, with the shortest path to go. For example, students want to go to canteen, lecturer gonna go to dormitory and classes. So in this presentation, we're gonna expose the algorithms for adaptive and efficient navigation. So which is 5 of them: A star, Digestra, Bellman-Ford, Kruska, and Branch and Bound. So in this presentation, we're gonna select optimal algorithm for adaptive and efficient navigation. So let's go.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Ajib Bezizi. Today, we are going to talk about our key findings in algorithm analysis, where we analyze 5 algorithms to see which one suited best for our case study, which is Smart Campus Navigation System. The 5 algorithms are Kruska algorithm, Dijkstra algorithm, Branch and Bound, Bellman-Ford, and A-star algorithm. Okay. First, let's look at the first one, which is Kruska algorithm. What is Kruska algorithm? Kruska algorithm is a greedy method that builds a minimum spanning tree by adding an edges in its increasing weight. Why we use this? Because it creates a static campus map efficiently, and it's very excellent for laying out the core campus network, and its time complexity is OE log E. Next is a Dijkstra algorithm, which mean the algorithm find the shortest path from a starting point in a weighted graph. It ensure most fastest reliable routing for standard paths across the map, and its time complexity is OE log V, which is very good. Next, the third one, which is Branch and Bound. Branch and Bound explore solution by dividing and pruning the option. It helps us to avoid an obstacle, for example like a construction zone, but it is slower on a larger graph. The fourth one is Bellman-Ford algorithm. Bellman-Ford algorithm is good for an accessibility because it's the most dynamic algorithm for shorter paths, even with negative weight, and its time complexity is O and M. And the last one is A-star algorithm. A-star algorithm is the only algorithm that have an heuristic search on its algorithm, where it adjusts the routes in real time around dynamic obstacle, making it very scalable and adaptive for our main campus. That's the 5 algorithm. Thank you very much.
So we move on to the next one. Is why our group choose this algorithm. Before of that, my name is Muhammad Shafauzan Iswan. The matrix number of 07707075. Okay, let's continue. Why we choose is because first, all those algorithm is chosen based on the real-time pathfinding ability and adaptability. For example, A-star algorithm. A-star algorithm is very efficiently to find an optimal path, even if the condition suddenly change. For example, like construction zone or block paths on the campus. The second one is excluded simpler method like BFS or DFS due to the lack of constant handling. As this algorithm explore blindly and don't prioritize optimal paths under specific condition. The third one is more complex of AI and method learning methods omitted due to the scope or complexity, which means that some advanced AI and machine learning approach like information learning or natural networks could offer even smarter pathfinding. That's why we will choose all those 5 algorithms for our assignment.
Hello, my name is Muhammad Daniel bin Wan Hilmi, number matrix 0774, and today I will discuss about our analysis decision. So, when we are developing the smart campus system navigation system, selecting the right algorithm is paramount. To do this effectively, we have made several analytical decisions as detailed in our report. First, campus as a sparse and weighted graph. The first fundamental decision was how to model our campus. We consistently represented the UNIZA campus as a weighted graph. So locations like lecture halls or library or classrooms are vertices, or nodes and pathways are edges with weights that correspond to distance or travel time. As seen in our analysis of the Dijkstra, Belmenford, and A*, we assume the campus graph is relatively sparse, and this can be seen in real life. So this justified the use of an adjacency list for graph representation. The choice is more space efficient, typically OV vertices plus edges, than an adjacency matrix for sparse graphs, and directly influence our space complexity and the efficiency of iterating to each neighbors of vertices. The second, the focus on relevant complexity and real-time needs. So we didn't pick just one scenario. We pick for our algorithms, we pick 3: best, worst, and importantly expected or average case. This provides a more practical understanding of an algorithm performance on a campus navigation. So a critical factor guiding this was our system core requirement for real-time data integration for our case study, which is handling dynamic updates like construction zones or accessibility constraints. Finally, emphasizing key time-space trade-offs. We have in our analysis we have deliberately highlighted time-space trade-offs that are relevant to a campus navigation app. For example, with A*, we discuss catching heuristic values, so that this can speed up pathfinding, therefore increase time efficiency. But it also requires extra memory, which is the space cost. Similarly, for Dijkstra, using a simpler binary heap versus a more complex Fibonacci heap was a trade-off between implementation ease and small performance gains. For Belmenford, an early exit optimization can save time without added space cost. Understanding these trade-offs is vital for a system that might run on mobile devices. So in summary, these decisions such as modeling the campus as a sparse graph and evaluating the complexity case with a focus on real-time adaptability and considering the practical time-space trade-offs provided a framework for comparing algorithm like Kruskal, Dijkstra, Birch-Bound, Belmenford, and A+, ultimately leading to our recommendation of A* to be perfectly suitable for our case study. Thank you.
For this project, we practice our group autonomy and collaboration. Each member was responsible for analyzing a specific algorithm. We communicate using WhatsApp, Google Docs for our report, and have daily meetings to stay on track report. We also have any conflict, which is one of our members is not using brute force because he said that it's not it's not practical for our case study because it's slow. And also one of our member have a conflict about using greedy algorithm because he said that it's too many greedy theory in this report, so he changed into Bellman algorithm. So we solve it together through discussion and agreement to ensure a steady progress. We set internal deadlines and made sure everyone was accountable for their roles. So that's all for our growth autonomy and collaboration.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Nur Hakim bin Norman. I will present about the choice of our teammate for the most stable pathfinding algorithm for the smart navigation system. The intelligent solution is designed to provide optimal real-time routing across a dynamic campus environment. Okay, in a system like smart campus navigation, selecting the right algorithm is critical. We need something that not only finds the shortest path but also adapts quickly to changing conditions such as construction zones or accessibility needs. Okay, we thoroughly evaluated several popular pathfinding algorithms like Dijkstra, ESTA, Bellman-Ford, Brush and Bound, and Kruskal algorithms. Each brings unique strengths and limitations. Dijkstra algorithms guarantees the shortest path and performs well in static environments. However, it lacks heuristic guidance, making it slower in dynamic, real-time conditions, especially when the entire map needs to be re-evaluated frequently. And for the Bellman-Ford, handles negative wakes and supports accessibility constraints effectively. Yet its times complexity of O (NM) makes it significantly slower and less efficient for real-time use on campus-scale graphs. Okay, for the third one, which is Brush and Bounds, it offers an elegant theoretical approach and can deliver optimal results. But its exponential time complexity in complex scenarios make it unsuitable for real-time navigation in a constantly changing environment. Okay, next we go to the Kruskal algorithms. It is great for creating the initial network layout or infrastructure, like building a minimum spanning tree. However, it's not designed for real-time pathfinding and lacks route optimization features. After detailed analysis, the A-star algorithm stands out. It combines the strengths of Dijkstra guaranteed shortest path with heuristic guidance from best first search, making it highly efficient adaptive. A-star offers expected time complexity between O, D and O, B, the power of D, where D is the depth of the optimal path and B the branching factor. Its space complexity is O (n plus E) with n as the number of nodes and E the edges, both manageable within a campus-scale system. In summary, A is the most balanced and efficient algorithm for the smart campus navigation system. It delivers accurate, fast and adaptive pathfinding, ensuring a smooth experience for both students and visitors navigating the campus. Thank you for your attention. I'll now be happy to take any questions or discuss implementation details. Thank you.